During 150 years of development, railway signalling has sought the perfection of total fail-safe reliability. From early days, the operation of points and signals were mechanically interlocked to prevent signalmen setting up conflicting movements in error. Later, electrical locking was introduced to ensure that signals could not be cleared while the section ahead was occupied. Finally, the adaptation of the simple track circuit to become an integral part of the signal control operation resulted in the modern multiple aspect track circuit block. Mechanical and electromechanical interlocking has now given way to computer-controlled, solid-state electronics in the latest installations, such as this one here at London's Liverpool Street. All this means that signalling has virtually reached that goal of fail-safe reliability. The system simply will not permit human error. However, as the whole purpose of the signalling system is to regulate and control the movement of trains, total fail-safe reliability cannot be achieved unless the system is able, in the final resort, to physically retard or stop a moving train. Let's put it another way. The signalman is protected against the consequences of error, as we've already seen, whereas the driver may still fail to respond to indications given. Certainly the AWS goes part of the way, but once its warning indication has been cancelled by the driver, he is still open to distraction, error, or misjudgment. This is where automatic train protection comes in. Let's begin by looking at what it doesn't do. It doesn't in any way automate the train driving function. The driver still drives the train in the normal way, utilizing all those human skills, which no automated system can satisfactorily simulate. So what does it do? Well, firstly, it advises indications about signaling, approaching speed restrictions, and the maximum safe speed at which the train may run. If the train is being driven normally, the ATP equipment will do no more than provide the driver with vital in-cab information. The second function is that of warning. If the driver allows the train to run at a speed higher than conditions permit, the equipment will indicate that action is imminently required. Should the driver fail to respond to the warning given, the equipment will then enter its third function, intervention. It is only at this critical point that control is taken away from the driver. It's now time to look at how automatic train protection actually works. Information is transmitted to the train from line-side beacons, which are situated on the approach to each signal, and in other locations, such as on the approach to speed restrictions. A beacon consists of an electrical conductor formed into a loop and laid in the 4-foot way. The loop is supplied with an electrical signal from a line-side transmitter. Loops vary in construction. On the left, we see a short beacon formed from steel tube. On the right, we see a longer beacon, generally known as a track loop, formed from electrical cable. Unless the train is over a beacon or track loop, the train equipment cannot receive messages from the track. Thus, track-to-train communication is intermittent, and signal aspect information may not be updated immediately. That's a problem that we'll come back to later. The data transmitted by the beacons is picked up by an on-train receiver located underneath the driving cab. The encoded information is then transferred to the onboard computer, where it is referenced against train data for length, weight and brake force, as well as speed information from the on-train tachometer. So we can see that the onboard equipment consists of 3 components: the receiver, the computer and the tachometer. At the heart of the system is the comparison of actual speed against the permitted speed and against speed distance curves. Firstly, let's look at supervision of line speed or maximum train speed. If the train is travelling at the permitted speed, the ATP equipment takes no action other than providing indications. If the train speed exceeds the permitted speed by 3 miles per hour or more, ATP provides a warning. If the train exceeds the permitted speed by 6 miles per hour or more, ATP will intervene by making a brake application. The tolerances of 3 and 6 miles per hour allow the driver to drive confidently up to the permitted speed, knowing that ATP will not interfere. Secondly,
Let's look at supervision of train braking to a target, that is, to a reduction in permitted speed ahead. The onboard computer calculates three speed distance curves: the indication curve, the warning curve, and the intervention curve. As we can see from the graphic, a train travelling at or near a maximum permitted speed of 100 miles per hour at A is required to reduce speed to a maximum of 40 miles per hour at B. By referencing the train data to the line-side data, the onboard computer calculates three speed distance curves. The first is the indication curve. The second, the warning curve, commences at the current limit plus 3 miles per hour and terminates at the target limit plus 3 miles per hour. The third, the intervention curve, commences at current limit plus 6 miles per hour and terminates at target speed plus 6 miles per hour. The indication curve is used to determine the indication point, the point on the track at which an indication of the target is first given to the driver. Let's look at the supervision of braking in more detail and plot the actual train speed. Where the train passes the indication point, the driver is advised of the new speed ahead, in this case 40 miles per hour. If our driver brakes the train without crossing the warning curve, the ATP equipment will simply continue to advise. However, should our driver permit the train speed to exceed the warning curve, the ATP equipment will immediately warn that action must be taken. The driver still has full control at this stage. Should the action be insufficient to prevent exceeding the next curve, the intervention curve, the ATP equipment will intervene by making a brake application. The driver will be unable to release this application until the train is brought below the warning curve or reaches the target speed at B. Now let's have a look at how the system works in practice, beginning with the ATP display on the driving desk. At the centre is an analog speedometer. In the centre of this speedometer is the 3-character display window. This display window indicates the nature of protection being provided by ATP, or gives the reason for a warning or an intervention. Around the circumference of the speedometer, at 5 miles per hour intervals, are the green permitted speed lights. One of these may be lit, as here at 100 miles per hour, to indicate the maximum speed at which the train may be driven. However, if the green light is flashing, as here at 40 miles per hour, it indicates a lower target speed which must not be exceeded at some distance ahead. Outside this ring of green lights is a ring of yellow lights, also at 5 miles per hour intervals, but only up to 50 miles per hour. These are the release speed lights, and one may be lit, as here at 30 miles per hour, instead of a green light on the approach to a signal at danger. Release speeds are used to overcome a problem of intermittent communication. Put simply, the onboard computer may be unaware that a signal, which was previously at danger, has now changed to a proceed aspect. If the computer carried on supervising to 0 speed, the train would have to virtually stop at the signal, even if the aspect had changed to green. The release speed is the speed below which ATP no longer supervises to the warning or intervention curves. The release speed is required only when the train is between beacons and the computer cannot be updated with the latest signal aspect information. A release speed is not shown if the ATP train equipment is over a track loop. In this case, the onboard computer knows the aspect of the signal. Below the speedometer are 4 illuminated push buttons of different colours. From left to right, they are marked brakes, pass stop signal, shunt, and on. The 2 centre push buttons have hinged covers to prevent accidental use. The best way to appreciate the actual operation of the system is to see it working. So let's put ourselves in the driving seat and take a run over a 4-aspect signalled line under full ATP supervision. For simplicity, we'll assume the minimum ATP equipment on the ground, a beacon at each signal. At the moment, we are running under clear signals on a line with a maximum permitted speed of 110 miles per hour. We can see that the permitted speed light at 110 miles per hour is illuminated. The display window is showing 3 equal signs indicating that we have full protection available in an ATP-fitted area. This indication also means that we are not being supervised to stop at a signal at danger. As we approach the next signal, we can see that it's showing double yellow. As we pass the signal, the display window changes to 2 zeros, indicating that we are now being supervised to stop at the next signal but one. A single blip gives audible indication of the change in display. When we reach the indication point for the signal at danger, a further blip sounds and the steady green permitted speed lamp at 110 miles per hour is replaced by a flashing green target speed light at 0 miles per hour. This indicates that the signal at danger is the most restrictive target, more restrictive than any other speed restriction that may be in force. We are now approaching the next signal at single yellow. As we pass the signal, the display window changes to 3 zeros, indicating that we are being supervised to a stop at the next signal. As we approach the next signal, the flashing green target indication at 0 mph goes out and is replaced by a steady yellow release speed light at, in this case, 25 miles per hour. ATP shows this release speed because it doesn't know whether the next signal is still showing red. Remember, the train is still between beacons, so cannot be instantly updated for changes in signal aspect. As we draw up to the signal, it does indeed change to single yellow, so we can continue. But of course we must keep our speed within the 25 miles per hour release speed to avoid warning and intervention. We must also remember that the display of release speed is not an authority to pass the signal. If the aspect had not changed, we would have to stop in the normal way. If we inadvertently went past the signal at danger, ATP would have made an emergency brake application. On passing the signal at single yellow, the onboard computer receives more information from a beacon. ATP now knows that the signal was not at danger and supervises so as to stop at the next signal. Thus the indication in the display window remains at 3 zeros. The yellow release speed light is no longer required and has gone out. However, the train has already passed the indication point for the next target, the signal ahead, and so the flashing green light at 0 mph has reappeared. So far, we have driven the train within the speed requirements of the ATP equipment. We have simply been advised of the circumstances and the display window has shown steady indications. Now let's see what happens if we allow the train to exceed the speed requirements. We now pass a signal showing double yellow. The steady green permitted speed light changes to a flashing target at 0 mph as before, but we make no attempt to brake the train. As soon as our speed crosses the warning curve, the green light goes out. The display window starts flashing and a warbler sounds continuously. We must now apply full service braking if we are to avoid intervention. When we have brought our speed below the warning curve, the normal indications will return and the warbler will cease to sound. All is well. Now let's look at the extreme case, intervention. We have just passed a double yellow aspect. The display window is indicating a stop at the signal after next, and the 0 target speed is indicated by the flashing green light at 0 miles per hour. The speed crosses the warning curve. The flashing light goes out. The display window flashes, and the warbler sounds. However, we still make no attempt to brake, allowing the speed to cross the intervention curve. At this point, the ATP equipment initiates a full service brake application. The brake push button lights up to advise us that intervention has occurred. This brake application is maintained until the train speed has fallen below the warning curve. When this happens, the normal indications return and the warbler ceases to sound. The brake push button begins flashing to tell us that the brakes may now be released. This is done by depressing the brake push button. We have now regained full control of the train. What we have looked at so far in this brief introduction to ATP is called full supervision. That's to say operation over a line equipped with 3 or 4 aspect signalling, where the ATP covers supervision to each signal as well as to permanent speed restrictions, temporary speed restrictions and emergency speed restrictions. There are 6 further modes of operation. 2 of these are supervisory. Partial supervision, which provides limited protection when the full supervision mode is not available, and shunting, which provides for low-speed movements without train data being entered. Other modes cover equipment self-test, entry of data describing the characteristics of the train, temporary isolating the ATP equipment during special conditions involving propelling, single line or emergency block working, a special failure mode which forces the driver to isolate the equipment. A full explanation of the modes will be given in our next film, Automatic Train Protection, the Driver Training Module. However, one mode deserves special mention now, the data entry mode. Like any computerized system, ATP can only function properly if it is fed accurate data. So here is a new and vital role for the driver, the entering of precisely accurate train data into the onboard computer. Some of you may be concerned that ATP will mean a lessening of the driver's role in terms of skill and responsibility. This is simply not so. ATP should be seen, instead, as the application of modern high technology to assist the driver and give him and his train additional protection against the results of misunderstanding, misjudgment, or error. Where a train is driven normally, within safe parameters, ATP will do no more than keep the driver informed of the vital speed features of the line and the state of the signalling ahead. It should be seen as giving the driver that security that has long been commonplace for signalmen. Driving over ATP-equipped lines may involve some modification of braking technique to avoid, where possible, provoking warning indications or actual intervention. Generally speaking, however, you should find train handling much as before, but with the added security of really comprehensive information on the state of the line ahead. In the near future, 2 pilot installations of ATP will be introduced on the Great Western Main and Chiltern lines. Each line will be supplied by a different manufacturer, so there will be detailed differences in the equipment used, for example the beacons. However, from the driver's point of view, operation and display will be identical. The pilot installations will provide valuable operating experience of ATP on your own particular railway and will give you the opportunity to play your part in the shaping of the national system. The future will see the introduction of comprehensive ATP to all busy trunk routes and busy commuter lines, while secondary lines will have a more selective application covering certain key signals and speed restrictions. All this adds up to some big pluses for our industry, safer operation and higher speeds available with existing signalling. Whether it's intercity, regional, or commuter passenger, or long-haul freight, it all adds up to a great increase in our competitive edge in those 2 areas where we already score heavily, speed and safety.